Good afternoon. Welcome to TEDAI Vienna. I'd like you to imagine a world where every complex technical and industrial challenge, from designing safer airplanes to modeling and understanding complex energy systems, is solved not in months or even sometimes years, but in seconds. That world is closer than you think. We often think about AI in terms of data and algorithms, or using Nano Banana and Midjourney to turn your dog into a talking podcast host. But what happens when AI meets the laws of physics? For the next hour and a half, we're not going to talk about viral trends or Studio Ghibli or using a custom GPT to fix your washing machine. Mine does that. Or to teach and tutor my children German, does that as well. But instead, we're going to talk about how reshaping entire industries through the AI lens of physics becomes possible. And to do that, it's my pleasure to be joined by Johannes Brandstetter, who's the chief scientist and co-founder of Emmi AI, and Carlota Alcázar, who's the VP of People. So please welcome them to the stage.
Sure.
Yes, I'm here today. But before we talk about them, we want to talk about you, because it's always good to know who's in the room. So by a show of hands, and it's okay if there's multiple things that apply, we'd love to know if you'd raise your hands and tell us if you're, are you scientists, engineers, and researchers? Awesome. That's great. Business and industry professionals? Let me see, mix. And students and educators? Awesome. Great. Another show of hands. I'd like you to raise your hands if you've used an LLM or ChatGPT or Gemini or anything like that within the last, in the last week. Yeah, come on, right? Now keep your hands up if you've used it in the last 3 days. Keep your hands up if you used it in the last 24 hours. Keep your hands up if you used it within the past last hour. Keep your hands up if you're using it right now. Okay, good. At least we have somebody. So I'm George Nimeh. I'm your host and an MC for the next 90 minutes. I've spoken at a couple of TEDx events, including TEDx Vienna here 10 years ago. So this is a bit of a homecoming. I own a boutique consulting firm. I'm a Perplexity Business Fellow and a TEDAI Ambassador. And it's my honor and privilege to be with you here today. As I mentioned, Carlota is the VP of People at Emmi. And before we dive into the themes for today about technology and AI and physics, I'd love to know, and I'd like you to tell us a little bit more about yourself and what brought you to Emmi in the first place.
Yeah, thank you.
Welcome, Carlota.
Well, hi, everyone. My name is Carlota. I am from Barcelona, so this means that we will all enjoy my Catalan accent for the next hour-ish, I think. And yeah, before talking about myself, I want to say also thank you for having the opportunity of being here. It's a first for me, so I hope it's not too obvious, but I'm quite nervous at the moment. I hope it's gonna get better soon. And yeah, also thanks, George, for organizing this and bringing us here. And about myself, around 10 years of experience in people world / HR. And basically what I did so far is help companies to scale from around 15 people to 300, usually quite fast, and always tech startups. So I have seen, many things, acquiring other companies, being acquired, going through the classic round of layoffs that we all lived a while ago. And I joined Emmi AI around a year ago. And it's been an interesting journey, lots of learnings.
It's great. Thank you. Johannes is the co-founder and chief scientist. I like to call him the brain. It's always a challenging and interesting time to have conversations with him. There's a really fun guy to be around, actually, but also blows my mind. You've You're a physicist turned machine learning expert. You've worked with computer scientists like Sepp Hochreiter here in Austria in Linz, and Max Welling in Amsterdam. Before founding Emmi, Johannes worked at CERN, worked at Microsoft, and notably developed or co-architected Aurora. And if you're not aware of Aurora, it's one of the first foundation models that was developed for weather prediction, which I think has a nice symmetry and crossover here. But I'd like you to tell us about yourself in your own words. Give us your background. Tell us what brought you from academics to industry, and why you think AI and physics can change the game.
Yeah, first of all, I have to join Carlota saying thanks for having me. I mean, you did a pretty good intro already. Nothing more to add. Maybe interesting, I studied in Vienna. I studied actually physics here. And then I did my PhD at CERN. And as back in the days when high energy physics was still cool. And yeah, then I switched to deep learning as everyone who didn't see a future in getting a job in physics. That was also one of the moment or the connecting dots with which I have with Max Welling, whom I considered one of my biggest role models and close friends. I joined his lab in Amsterdam in 2020, and then he lured me into Microsoft research. And this was the nice idea where I saw everything from big tech, from change you can do when building large models, from the impact you can have in the community as of weather modeling, where this is going, how quickly you can change a community, but also how boring it is to work in a big tech company. And at that stage, I decided to do this revolution which we're seeing in weather. I mean, we saw a shift of the whole community within 1-2 years to bring it to the heart of engineering, where there are basically 50 trillion of dollars sitting around waiting to be turned around. And that brought me back to the real life, to the startup life. But I also have a second foot in academia, professor university. And this is, I think, where things close. Happy to be here.
It's great. Thank you. So we've got 5 themes that we're going to try to hit on today. We're going to talk about the founding of Emmi and its core mission, a little bit about the core innovations that sit at the heart of the startup that they've created. We want to talk about the real world impact. So to move from theory to practice and really discuss and hopefully get Johannes to kind of unlock and describe how some of these things work in aerospace or in engineering and other fields. We'll push him to kind of open up the secret box as much as you can. We want to talk about how we build a unique team and a culture in a situation like this, where we're looking at not just ML and physics skills, but also broad domain knowledge, and how we fuse those together into teams of scientists, researchers, and technologists to make that all happen, which is also, I think, for me, something new and something that must be challenging for you every day. We want to talk about the global stage, not just here in Europe, but how we as Europeans and startups and businesses can compete on both sides of the pond, as they say, and talk about the future and understand not just a vision for where Emmi's going, but also for us in this crazy new world that we're living in that changes every single day. But before we do that, or at least what I'm hoping and what we're hoping is that these next, whatever is 30, 40 minutes of conversation inspire you. We want this time to make you think. I think it's kind of a core vision of what TED is all about in the first place, but to use the time in our conversation here to think and to make you want to ask questions. And we're going to leave a good amount of time at the end for your questions. So I'd encourage you, as you hear us, hear yourself, and write something down or put something in your head. And although Johannes is a professor, but I won't dock you points if you use ChatGPT to formulate your question. But if you do, I need you to tell us the prompt that you used to write it. So it's allowed, and the professor here, I hope, won't take off too many points for question taking. That being said, let's get started. Let's start at the beginning. Let's look at the kind of understanding what this is all about. Now, I know there's a lot of folks in the room who are already in the scientific community, but for everyone else, or let's start with some basics. What is AI for engineering? What does it mean to simulate something in general? And why does using AI for simulations matter in the first place?
Oh, that's a tough question. That's usually what a VC asks you when you have the first call. I would say we have seen a few transition during the way we do our engineering. The first clearly big game changer were wind tunnels. So before that, people were testing, for example, airplanes in the field. So they were trying to fly around and find what works and what does not work on a plane. That's actually much better to do in an environment where you can control wind and basically how the wind is interacting with your plane and how you have to design your wings and so on and so forth. That in the last 30-40 years somehow slowly step by step went into computers. So nowadays we basically every device we have, every car we drive, every plane we fly on, every machine we use, every chip which is in our computer is simulated first, and not only simulated but designed by hundreds of engineering simulation cycles. And this simulation is costly, takes time, brings our computational budget to the limits. And this is obviously the next big frontier where AI comes in. Why? Due to many different reasons. First, we are much faster in simulating. AI is good at connecting things. We can put different simulations together. We can scale up simulations. We can interact with our simulations. And we see this change in the way engineers think about these problems arising, I would say roughly 3 to 4 years ago. But in the recent year, there has been a tremendous shift due to several unlocking phenomena that suddenly real world use cases like simulating power grid transformers, simulating planes is suddenly possible with AI in minutes, seconds, and not like days or weeks. And this is what it's all about.
So, but thanks. Oh, man. So I've heard about it being used for scientific research like materials design, controlling plasma and fusion reactors, solving Olympiad math problems. That's something I think that everybody kind of understands that this is where things are heading, and predicting the weather like you've done in the past. But how did that wrap up for the founding vision for Emmi? Like, I mean, there's a lot of places that you could have taken this, and there's a lot of places where simulation has value, or different verticals or different sectors of activity. Why industry? Why this place? You were in weather, for example, and working on really complex models. What bridged the gap, and what was the founding vision for the company?
So founding vision is always, you have that in hindsight, right? So you come together and then you realize that you like each other and that you think at the same thing. For us, it was more on the way that I came from weather. I saw this impact, and I really, with people at university, we tried to simulate very complex flow processes in industry, a factor of approximately 100 larger than what people at DeepMind did at the moment. Not with the best accuracy, but we saw some very cool results, and I was actually very driven by the scientific challenge of doing that. And then at some point I sat together with Dennis and Mix, so my two co-founders, and they were the first to really looked into that, and they did a market analysis, they looked at it, and they showed me, we were talking. And then at some point, Dennis said, Johannes, this is approximately 100 times cooler than building another LLM. And I said, I disagree. I think it's 1,000 times cooler. And yeah, from that on, we started talking, and that basically was our... So it wouldn't work with an entrepreneurial basically signature on the side.
It would or it wouldn't, I'm sorry. It wouldn't, right? Yeah. So Johannes has talked about the technical side, or the vision, and the reasons why we've come to where we are today with Emmi. But Carlota, from your perspective, what does it take to build a team and a culture to support a company like this, to build on that and to fulfill that vision? What are the human factors behind Emmi's ability to innovate at this level?
Well, at the end, it's kind of asking what is the secret sauce. What comes to my mind is kind of obvious. I It is like, even if we are all talking about AI breakthroughs, being fast, being the first, and so on, like at the end, people still make the difference, at least for now. And at the end, for us, what makes big difference is to get the right talent, but also in the right room. It's just at the moment we have people more from the machine learning part and more from the domain expert part, and then you need to make sure that they match and that they start doing this ping pong of ideas, and then at some point this cling magic happens, and then this is where you have the AI breakthrough. So let's not forget that point.
You told me that kind of working on classic talent development and in the software world where you had been, I think with Dennis actually prior, and you've moved into a world where researchers and scientists are, let's say, or physicists are kind of in the front seat, or at least in the co-pilot seat. How's that different? Yeah.
Yeah. I mean, almost 10 years of experience, and a year ago for me was like, welcome to the new world. Because I was very used to the classic recruiting, where you have a nice career page and then you look very cool on LinkedIn and so on. And now I realize that doesn't work, and that I cannot just post, I don't know, a job ad made by AI, obviously, and just pray to the gods of recruiting to just give me those leads, because some of them are like some of the researchers we're looking for, they are not even in any social media. It's like, if you're lucky, they have Google Scholar. So actually I know a couple of people at the very end of the room that they only have Google Scholar. If you type their name in Google, you won't find them except for the Google Scholar.
That's interesting.
So for me, this is a big change of how we hire people. And I just realized that it's better if you work on networking, on knowing the type of universities that we need to work with, and just make sure that you know the right people instead of doing fancy, shiny stuff on LinkedIn.
That's fair enough. We'll come back to this in a little bit. The CEO of DeepMind, Dennis Hassabis, who's the Nobel Prize winner, I think his name is pretty well known in the room, said recently, I do feel like we'll have AGI in the next 10 years, full AGI. And I think that it will usher in a new golden era of science, a kind of new renaissance. And he used the word renaissance, which I kind of enjoyed listening to. And so with that in mind, Johannes, can you give us a rundown, kind of help us understand what makes Emmi AI's approach to simulation unique? Tell us about the UPT, help us understand how you're making this a renaissance.
I'm not so sure if I would agree with Dennis on that. For them, AGI is related to text and to images and to basically, a bit to medicine and biology. But the engineering world is very, very different. There are three factors which you usually have to make breakthroughs. We saw that firsthand in weather. I realized that also in hindsight. The first, if you have scalable architecture, scalable models, scalable compute centers. We have that. We know basically how to build computer vision language models. I mean, that's easy, right? Then there is the data aspect. Data is abundant. We can scrape the internet, and then there is a way of what do people actually want? What does an engineer want? That's also easy in language, because a person wants to have the next word predicted. Because if you do that over and over again, you generate text. But in language and engineering, this is very different. So first of all, if you try to mesh a Formula 1 car the way a CFD engineer is doing it, you need a billion of mesh cells, a billion. And then run a computer simulation on this billion of mesh cells with a high resolution turbulence model like large adder simulation. This takes a supercomputer to simulate one of these cars. Then this data is not saved, it's not publicly available. So every company has their own set of data, their own set of solvers sitting on the data, but it's not publicly data out. And then you actually don't know what you optimize for, because AI is different than classical tools, and you would use AI differently because that's where it unlocks the power. So neither of these three aspects is basically solved. So scale, data, and basically optimization for metrics. I think what we really cracked, and we see that from the impact we get from industry and from VCs and from other companies, is the first. So we can scale our tech to problems like Formula One. I mean, we actually have a Formula One customer, to airplanes and to all that stuff. That generates excitement, but that's just the first wave. The second wave, and this is the more challenging wave for me, is the data wave. This is the wave where you have to build your own gold. It's not, you cannot just stick for gold. You have to be the one building the gold. That's what we are actually doing, and that's where the next breakthroughs will be coming.
You mean in terms of your own foundation models?
You have to generate the data you train the models on.
Yeah.
Right?
So explain to us then. I think everyone knows what a GPT is, but you guys have developed what I think is called a UPT. So is that right?
Yeah.
It's a universal physics transformer. Can you explain that as a scientist and then explain it to me?
Obviously. So if you look at the whole worth chain in deep learning, it's very easy actually. So there is this, everyone uses chip from NVIDIA, manufactured in TSMC in Taiwan, built on the ASML machine of the Netherlands, and everything is optimized to run on transformers, which is the best and only architectures we have, and this will stay for the next 5 years. Done. And the thing is, we know how to use transformer for language. I think that's where the billions and billions and billions of dollars is happening. We know how to use transformers for language, text, and so on and so forth. But we don't know how to use them for engineering. To a point where it gets a bit ridiculous that this complexity of quadratic attention and what to look at. Yeah, and basically what we did very extensively, which also coming from my time at Microsoft, we were looking how to scale these technologies to look at these problems to be actually applicable to engineering problems. And we had very, very smart people who found a way to do an full airplane with more than 1 billion of mesh cells on one GPU with a transformer architecture. And that's obviously then the equivalent to saying, okay, I can train a model on like 1 million context text in language.
Can you translate that to the room who aren't the scientists? Try.
So we took the language on which GPUs, graphic processing units, are programmed to make it applicable to engineers.
So, as I've understood it, with my this much understanding of how CFD works, you have a coarse or a fine data set. In other words, the data is either better or worse, more or less, and you use that to model something, right? Let's say you're going to figure out whether or not this is a corner or not. And to figure out if this is a corner or not, if I'm using a fine mesh of data, it means I've got like points that start here, and every single point as fine as I can possibly make it around the corner, so that the thing will say it's a corner. And the way I've understood what you're doing through what I think are called anchor tokens or something like that, is that you take a set of data and you either kind of start here on the corner where it's here, 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 and here, or potentially 2 times as many, 5 times as many, 100 times as many, but never all of them, and then ask a transformer if it's a corner or not. Is that close?
Yeah, I can. Very, very, very good. I mean, just why you need so many tokens or so many mesh cells if you want to mesh such a Formula One car, because the physics is so complicated in order to actually calculate the physics, discretize the space. So you need this tremendously large meshes, and this is where the numerics run. If you make numerics go for a car, which is much less triangles, then you just don't model the right physics. And if you go to the street or to the wind tunnel, it's not what you're modeling. And that's why you need these many mesh points. And actually, the idea with deep learning is to be very sparse with this input, because you don't need all of them. You basically let the model decide what it needs, and then it turns out that actually it's not so hard to put a Formula One car on a GPU.
It's a good segue. The word sparse, by the way, I've read about a few times. You guys can put it into your favorite LLM and understand sparse and ball modeling, I think, as a piece of the puzzle. But that's probably a step too far for today. But speaking about F1 does help us come to let's say, the more real world applications of what it is you're actually doing. I spoke to Dennis Just, he's the co-founder with you, like you mentioned, the CEO of the company. He talked about securing enterprise contracts in aerospace and semiconductors. He said that you've got real world 7-figure projects that are running. And so can you give us a couple of those? Can you talk to us about, can you name names as much as you can? And can you describe to us, both in scientific and real world terms, what it is you're doing and for who?
So that's the problem, and Dennis is not here. I don't know what I'm allowed to say, but
I talk to him, and you can say anything you want.
So what we are certainly doing, and this is a prime example for me, and this is I would want to give anyways. So we have a power grid transformer provider. So the power grid transformer are these large machines which actually turn high to low voltage and vice versa. They are super important for the whole energy grid. And these transformers are the backbone of modern compute center, modern way we deposit our energy. And this is, if you look at the stock prices of some of these companies, like General Electric, Siemens Energy, Schneider Electrics, they're more steeper the curves than NVIDIA. I was also not aware of that until recently. The thing is, these power grid transformers are tremendously important because there is like the net worth in the German power grid network is I think close to $1 billion. Don't quote me on that. Just by the energy which is shifted around. And these power grid transformers, the problem is that you have to make the guess right on the gap of voltage you use them, because if the gap of voltage is too large, they heat up, and it's not good if a $200 million machine heats up. However, if the gap is too small, you lose a lot of energy or a lot of money because the voltage you cannot convert. So what you actually need to do as a power grid transformer company or as an energy company, you have a very good real-time estimate how you run those beasts. And what you then do, obviously, when you need an estimate, you go to the computer, you simulate this stuff on your computer. The problem is only that to do a proper simulation which works for reality, it needs approximately 3 to 4 days, but you need the decision in a few seconds, right? And the cool thing is that the company which we're working on, they went to a few other companies and tried to solve that. And we could actually really solve that. So we can simulate these beasts in real time. And that obviously makes a big impact. I mean, it's a digital twin, right? You have a real-time answer to the network, and you can make your estimates how you run those much more aggressively. So this is, I would say, one of the prime examples. You want more?
I'd love another one. Yeah, I mean, I've got a couple comments on the electricity piece and efficiency, but maybe let's stay there for just a second. So the value is in the time it takes for you to make the calculations and the speed at which they're able to change the way they're optimizing the grid itself. Was that what you're doing?
The value deposition for the company is that you can use like the gap of high to low voltage or vice versa is approximately 20% higher. They can run this stuff now, which saves a lot of money for the energy grid.
Yeah. So I had this later, but I'm going to use it now because it seems to make more sense. It said the Stripe's CEO Patrick Collinson said the limiting cost of intelligence will be the cost of electricity, and that was echoed by Hugging Face's CEO Thomas Wolfe. It seems as though that's part of this particular project and piece of work, but I'd love to know just your general thoughts on that.
Yeah, I mean, I can only guarantee. I would say that the limiting cost is in you need to build this stuff. We are just not ready. I mean, they all these companies, they have a backlog of 6 years of delivering these devices because everyone builds compute centers like crazy. And then these things need to be more efficient, but nobody thought about how to make them more efficient because doing things conservative was always enough. But now, if you have a backlog of 6 years, you need to make your things more efficient. You need to make your transformers more efficient. So that's a prime example of AI for engineering. And suddenly, if you have this pain point as a company, as an industry, you're suddenly getting innovative. You suddenly call companies like us because this is what helps to speed up engineering cycles.
So I race motorcycles, or I used to at least before I crashed. I've worked alongside Ducati for years, and I know that in MotoGP, for example, the difference of winning or a losing round is sometimes a hundredth of a second. The precision in terms of the engineering that they use for MotoGP bikes is extreme. I'm imagining that that's either the same or even more in Formula One. And without talking about the team, I know that you're working with one of them. And can you describe what it is that you're doing?
So Formula One is really the prime of engineering. There, for many reasons. I mean, it should be in a way that what you can simulate in Formula One is what you test in the wind tunnel, and different small changes make a big difference. Why this is from a CFD aspect, Formula One is one of the very few examples where minor changes lead to a different behavior in the flow field. So there is this famous example of this one team. I'm so bad with Formula One, I have to admit, although I lived next to a racing track in the Netherlands for 2 years, but they... Sanford.
Sanford.
Next to the sea. So what they, I think it was Mercedes, but I don't know. What they realized by accident, actually, that if you do the setting a bit different, you get a huge turbulence behind the car. And what causes this turbulence is then whenever another car tried to overtake a Mercedes, they get like this, and they had to slow down a bit, which was a massive advantage for them. And this is just a tiny change in the chassis, which basically made this effect. So these tiny changes in the geometry have dramatic impact. And that obviously means that simulations have to be super accurate. You only have a few CFD measurements which you can use. So and there is always the looking for the sky to use new technologies, and that's obviously why Formula One is very attractive for these technologies.
So what are you doing?
Yeah, we are combining simulation, real world measurements, and trying to get better wind tunnel experiments.
So from my layman's perspective and movie fan, I mean, I think we've all, or a bunch of us, have probably seen the films that are out there, including the new one about Formula One, where you see aerodynamic chambers. I think we kind of can all picture this in terms of kind of airflow and testing. Is that what this is? Is that where this is? Is it for the engine? Is it for the aerodynamics?
Well, for the car.
It's for the car, right? For the chassis.
Yeah.
Yeah. So you're simulating wind tunnels, or not?
Yeah. Yes.
If it's not, then say no and tell me, because I'm curious.
We are combining. So that's the cool thing which you can do with these tools. You can combine simulation with measurements. So for example, you can think of the wind tunnel as a measurement, right? Because you can't put the sensor there, and the sensor tells you, okay, this is the wind coming in. That's the car. This is the wind which comes in. I know what I measured here, right? And on the other hand, you have the simulation on the computer, but the simulations don't need to be accurate, because whatever parameter is wrong, whatever meshing you did wrong, gives you a different answer. So the ultimate truth is to understand these behaviors, which is needed, is to combine all of this information, and that's the next frontier. And then the next frontier is to get rid of wind tunnels at all, right? To do everything in the computer.
Carlota, I'm coming right to you in a second. I just have one last follow-up with Johannes on this topic. And it's broader than just engineering and Formula One cars, but it impacts them as well as the other things, and that's trust. If you're going to put a new wing on a car before it goes and races at Monza, or you're going to run something at 350K, or you're going to develop a new drug, or you're going to optimize a power plant that impacts cities in terms of energy creation, it has to be trusted. I know that Emmi publishes, and I think that that's cool. I think that in the industry, or at least in a lot of the reading that I've done, there's less publishing in the new age, maybe for corporate secrets or venture capital. I have no idea why, than with classic mathematical modeling. So I personally applaud that. I think it's interesting. But how do you then engender trust? How do you get the trust of either a individual business partner that you're already working with, or a prospect to say, we can do this and you can trust our results?
I can't give you a good answer to that. I think what I want everyone to be aware of, that AI is not replacing simulations. AI is a different tool. So they are kind of orthogonal. So whatever you do as a company, you would need anyways both sides of the world, as well as we at Emmi need both sides of the world. So you don't trust an AI model in engineering. If you're doing it, you're probably not a very successful engineering company, and vice versa. You need AI to do different, like fast cycles and so on and so forth. It's similar to if you have an LLM and you say, okay, I need to write a very sensitive letter to my boss. You would also read the letter afterwards, right? And basically check what it was doing. And it's very similar with AI and engineering. So there is this interplay with simulations and AI, and therefore this is more an academic problem than a real engineering industry problem.
It's great. It's a really honest answer. I appreciate it, because I know in a lot of other situations it's like, no, we do it, we get it 100% right all the time. And I appreciate the idea that says it's not necessarily a replacement, but a complement and a way of acting faster, maybe more efficient.
Half of the people we have in our companies are the best engineers in the world. So if I tell them that it's a replacement, it would be a good company strategy, right?
Okay, so speaking about the engineers, speaking about the people in the company, what have you learned about the kind of talent that it takes to deliver this? What are the traits you look for in researchers or engineers that are different from a typical software, tech, or even an AI company?
Well, first of all, currently we only look for people who has a PhD, for example, which is something new for me. Doesn't mean we will keep only looking for people who has a PhD, but there's something that we look for. Also the balance between academia, but also looking for or being excited about applying your own research to the real world. I think if they are not able to combine both, we might not be the right people for them. Also, even though most of researchers know how to handle the unknown, they also like to have a very stable place where to work sometimes. So it's really try to be very transparent with them. So what we know, we really tell them, like, hey, we really know this. And what we don't know, we explicitly say, we don't know that. But we will, hopefully, by this date.
So you do that before or after they sign an NDA?
Depends. Yeah. No, I try to be honest anyway with them, even during my interviews. And this is one of the main traits I look for, that they feel okay with some of the unknowns. And also, a learning for me is that plenty of people who spend decent amount of years doing their PhD, they are very used to work alone, like by themselves, kind of lonely wolf, but in a good way. Like they get obsessed with something, and then they can change the world. And then you ask them, okay, can you join us and then work with the other brilliant brains so that you all together can make something even better. So I think it takes some time for them to adjust, and it's also something I bring proactively to say, how do you see it? And some of them actually appreciate that moment of self-reflection, because maybe they didn't realize, like, yeah, I'm very used to work by myself. So, yeah.
So this isn't a criticism of academia, because, you know, I've been to university and MBAs and the rest, but do long-term academics have a problem with pace? Do you have to warn or push or talk about speed and the ability to move fast and not necessarily break things, but the pace that you need at a business like Emmi? And I asked both of you that question. Maybe Carlota, you could start, and Johannes, you can follow up.
Of course, academia has this type of fame somehow of sometimes being slower, but you also have this in many other companies that are huge and super slow. And then you interview some people, and
believe that
sometimes takes forever for them to deliver something. So we're aware of it, and we bring it to our chats with the candidates so that they understand what to expect. But I think this can happen with anyone else that we hire. And this is where also our values come in, and we try to explain them how we work from the beginning.
That's cool. Johannes, you're kind of on both sides, right? Because you're still in academia and you got a company. So where's that balance?
I can only say, I would rephrase the question. Where do you find brilliant people who don't have a problem with speed, who are actually hyper speed, and who deliver much more than expected? And I would say, if you look through our board, who are people, we have people from Harvard, we have people from Oxford, we have people from Cambridge, we have people from Linz, we have people like who never ever left Upper Austria, and all of them are super brilliant in their own ways. So I think there is no concept of where you find brilliant people and where you find the people you need. It just I think a matter of recruiting, a matter of having a network, a matter of attracting talent. And actually you have, if you're in the startup, you have to set the bar very high. So you have to look for people who are actually all in on what they're doing.
So on that, in terms of the recruiting process, or at least in terms of how you find people and discover that, because I think it's these are personal traits as much as they are academic traits in terms of the people that you're looking to work with and the culture and the team that you're trying to build. How do they think? How do you figure out how they're thinking when you're interviewing them? What's the hiring process? I wrote this, how have you surfaced exceptional talent that impacted something in the real world? How do you find that out in an interview process? Is it just through discussions? Is it showing, not telling? Give us an example or two.
Well, I usually try to slice it in different moments. One is to find out what do they know and how good they are. Obviously, we can always check what are their papers and so on. So this already gives us a sense, which in other industries is a bit more difficult. And also here, Johannes helps me to understand what to look for. Then, I mean, we can all use AI tools for our interviews, obviously. So we somehow are going back to the old school mode to ask people to just come to visit us in the office and just all of us leave the laptops outside, because it's not fair if I ask you to not bring your laptop and I'm going to have my AI tool to make you uncomfortable questions. It's kind of not that nice. But we all leave the laptops outside and take a beautiful technology called whiteboard and just think. So we show them, I don't know, current problems, so they can also understand what they will find when they join us and just see how they think. And then they can also ask us questions, because this says a lot about what's crossing their mind. Of course, we cannot know everything. It's also when you get to know someone, I don't know, your partner, you also don't know everything from day number one, but you can get a sense and go back to this authentic way to speak with each other.
Yeah.
And this is not saying no to AI tools, it's more use it as a support, but for us, we just want to find out what's going on up here. And then we make sure when you join us that you are totally convinced.
And we have a lot of people where I said, Carlota, I want this person.
Yeah, this as well.
Where really you've kind of said, this is an interesting individual, let's go attack.
Yeah, many times.
That's great. And that's from reading papers, being introduced. You have the time. I mean, it's like...
Yeah, I mean, I'm very well in this whole academic. I'm connected with my time at industry, right? Yeah. I know people from DeepMind, Microsoft, and all the other labs. I mean, there is not a lot of universities who do the same, who do similar stuff. So, for example, ETH Zurich is pretty big. Sid Mishra, who is the godfather of simulation, ETH Zurich, is a close colleague of mine. Is actually an advisor to Emmi. We have the Niels Surrey group in Munich. We have groups in Cambridge and Oxford. And this is basically the simulation. I forgot Paris.
We'll get there.
This is the simulation space in Europe. And if you have your ties there, you actually know what's going on and what are the people that are brilliant.
This is great. You just said the word simulation and space in the same sentence, and my next question is about black holes. Which is good. Because one of the things that caught my eye as I was doing some background research was they've shared projects, or at least thinking, around simulating black holes. I saw a video and a post and a little bit of a discussion around it. Help me. Can you explain it? I think it's easier for you to talk about this rather than me kind of blabbing on. The question is, how does stuff like, and then, how does science fiction or how do things like that feed back into your core industrial work?
This is done at university, so I have to give all credits to Arthur's persons, Sandeep and Andre from Manchester. It's a cross-European collaboration. Basically, the idea was nobody has ever trained a neural network to simulate the black hole. So we just did it. And yeah, we got some emails from NASA. They were actually quite interested on that. There's a lot of brilliant people, and if you put these ideas out, they're jumping on that. Yeah.
You worked with, or you've spoken a lot with Neil Ashton, one of the guys who, but if you're looking for a follow-up to this talk, you should go look at Neil Ashton's a podcast interview with Johannes. It's also fascinating. It's a deeper tech dive. I thought it was really interesting. He worked at NASA, or at least with NASA at some point, right?
He worked with every big CFD company. He's now at NVIDIA.
So what does he think about? What would he think about the simulation of this black hole using NASA data? Does he agree? Does he think that it's correct? Is it right? How can you know?
I mean, that's part of the challenge, right? One thing, we are living in a triangle, right? So we have the reality, we have which is described. We describe the reality with equations, which we try to solve, but we don't know if the equations are correct. So far, nobody has found something which is against Einstein's equation. And then, so we have this gap between how we simulate our reality and then how we learn from the simulation. So there is like two ways of making error. So I think a big question mark is how to find out if what we are actually simulating and what we're training on, how correct is that? So, and there's things like energy conservation, mass conservation, and other laws of physics, which the neural network just has to obey. Or if you ask the neural network to make some predictions, you can check those predictions, and this is what it's about.
So here's my I don't even know if it's call it a challenge, call it a next question, however you want to put it. When I spoke to Dennis, we talked about the fact that AI is great at interpolation, but sucks at extrapolation.
That sounds like a CEO comment. Yeah.
The way I'll put it in dad jargon instead of CEO jargon. The way I explained it was AI hasn't invented the next Shakespeare. It's just written the next Shakespeare in the context of all the Shakespeares that have ever been written before. And so I asked for some questions online, and a guy who you might know, I don't know, he's a doctor from Germany, Martin Schiele, put it this way: how do you ensure that your physics AI simulations don't just optimize for what we already know, but actually discover new physical insights that we haven't thought of yet? And I'm pairing that back to the conversation of black holes, because how do we know? How can you know? And how can, if it sucks at extrapolation, if it can't make predictions, and Demis says the same, it's not really good at kind of inventing something new or discovering something new, how do we model what's not created yet?
There's many access to that. First, I want to say there is a phenomenal talk from Michael Jordan, not the basketball player, but the famous machine learning person, on interpolation versus extrapolation. Everyone look it up, because he basically says what's the certain limits of LLMs, what's the certain limit of AI in a mathematical form. It's tremendously highly recommended.
Great.
There is a few ways you can look at AI when you do engineering or when you do simulation general, right? The first is the generative aspect. So you generate something. The prime example for that is molecular dynamic biotech. So what people found out 30 years ago, when they wanted to make a new medicine and a new drug, they needed to come up with some estimates to test in the wet lab. And usually for 10 wet lab tests, 1 or 2 would be successful. So they needed a better suggestion of what could be a new drug. Because doing 10 expensive wet lab tests and only being successful once kind of sucks, right? So what they did is they came up with these first machine learning models which were suggesting new drugs, and then the positivity rate, so the successful wet lab experiments suddenly were raising. So in that case, AI was helpful in suggesting new things, but obviously not everything AI is suggesting was good, but it just increased the rate of success, and this is like it generated, so to say, a better understanding of molecules, and similarly you can think of it in the world of simulation. So you don't need to generate a new a physics system in most of the cases, but you need to generate a faster, better, more reliable estimate of what needs to be or what needs to be solved.
Yeah, I get it. Somehow, I said that when I was making my notes here, I wrote down that the approaches that accelerate existing models rather than revealing new physics. And it's still up here, but it seems to make some sense. Again, for me, the challenge when I come back to these issues is always about the borderline or that limit that we get to from understanding today versus predicting or inventing tomorrow. And what human creativity and what science and what scientists and researchers bring to the table in terms of inventing that future as humans, and what they bring to the table, accelerated potentially by the technology, but not limited by that technology's inability to imagine, to invent yet. And go from there. What sets scientists apart on a day-to-day basis? You said, you built these teams. I'd like to go back to talking about, working in an environment with mixed skill sets, mixed backgrounds, both from domain and machine learning, but also just from the basics of where they've done their education, what they've learned, what their focuses are. Compared to software engineers, you used the word black box with me once. Mm-hmm. Explain to me what that means.
Well, it's just looking back at my learning. So when I joined Emmi AI, I thought I've been 10 years of engineering, techie people, sure. Put them all, or I thought they are more or less similar. And then I found out, not actually. They are way more, deep into what they do. They basically have a big intrinsic motivation of solving things and nothing else than that. They also take things very literally. And this actually helps me, and now I found the benefit of you don't need to read between the lines. Just, you tell me something, cool. You disagree, perfect. If you agree, you will also tell me. So I don't need to rethink too much. I also think they really care also about the rest of the people, but they are not too vocal about it. So if you go and say, I need help, they will help you for many hours until they fix it. But if you go and try to make, small talk, you will have this awkward silence for 2 minutes, and then they will,
They're not that bad.
No. Sounds bad, but it's actually not. For me, even though, I see maybe the way I'm phrasing it is not great, but I think plenty of you connect with it and understand it. It's just different. It's we cannot expect. Actually, some weeks ago we were in one of these company updates that we do every week, because we are really transparent with everyone and explain what's going on. And I don't remember who was from the team, but put this beautiful long formula that I will never understand. I understand humans very well, but not that. And sometimes
maybe Stokes equations, but
might be. I don't know, and I don't remember. But sometimes we expect from everyone to communicate the way the rest of the world does, and at the same time you have brilliant minds that look at something in a very specific way. It's why should I ask you to communicate the same way I do? It's just find out other ways to communicate, and this was for me the biggest challenge since I joined Emmi, just in a good way. It's to me, I consider the employees somehow my product. I want to deliver them a good experience, and I had to explore what are their needs so that they can buy my services somehow. So this took me a while.
Fair enough. Is this news to you?
Wherever that.
What's your take?
What's my take?
Yeah.
What's my take?
that you agree with everything I said. Yes.
I mean, I desperately tried to teach my co-founders physics, but I also have to say one of these amazing things what comes out when people from different backgrounds, actually, it's not only engineering and machine learning, but also entrepreneurship sit together, is usually in Europe a scientist is trained to look at the problem where a solution exists and to make the solution marginally better. That's what we are trained on. An entrepreneurial person looks at the problem where other people are not even aware there is a problem. Because if you solve these problems, you have a big impact, because this is actually what is needed to be solved. But there is not a lot of open problems, because if a problem is open, everyone tries to solve it. The understanding, and that's connecting all these angles, is to find things that are unresolved, and to phrase them as a problem, and that's actually where these different mindsets and these brilliant people, the math, the science, the machine learning, but the entrepreneurship comes together.
Let's take that one half a step further while we're here. There's a follow up in a minute, but that. I think a lot about the multi-domain experience, about this idea of multifaceted backgrounds, whether it's in the scientific or research teams themselves, or just generally speaking in terms of how you're building the company. I've heard you talk about how video generation expertise, the people who are building VO3, or maybe even what's the new DeepMind's video product? It's also with 3. I can't remember. No, there's VO3. There's another model, the one that's allowing the Genie 3, exactly. Genie 3, it's allowing worlds to be generated on the fly instead of having models that it's actually creating from a CD that you're loading into a game box. It's actually just creating the stuff. And I've heard you talk about mixed skill sets, including what you're learning from video generation as it applies to the idea of creating simulations, or the way you're doing simulations. Is that part of the team build? And do you bring those skill sets in to augment the breadth of thinking from both ML and domain expertise? Or is that just, we read all the papers, understand what it is that they're doing, and try to learn and take that expertise and merge it into your thought processes or product?
It's more the first, that people basically interact and different skills get exchanged. There was also this amazing, I don't know if it was in the same weekly update, but one guy presented the stuff he did on a company project, or like we got a POC, and basically the POC was solved in a week, and it should be like go for 3 months. And he presented it, we are doing that, we get 1%, and so on. And I was like really amazed. I was like, who worked on this? He's talking about we, and then we did this and this, like 10 people were working on that. And then I said, what is we? And then he said, well, actually it's just me. But what I want to say is he managed in a few months to soak up so many knowledge from different sides, that he was able to combine that alone, and to solve this problem. And so this is really inspiring what goes on if you put brilliant people in a room.
I think it's the mix. One of the pieces for me is really that idea of the mix, that software developers over years past have I know there's also diverse skill sets in terms of what a development business looks like, for example, but the diversity of skill sets and the breadth of thinking for me is new. When I look at this age of companies that are being developed, and the types of information and backgrounds that you need to innovate on. How do you innovate on aerospace if you don't have somebody that knows about aerospace? How do you develop an ML if you don't have somebody that knows how to create an ML? And if you're only 25 people, even though you get funding and backing, how do you do that? I mean, how do you expand, and how do you understand that a team needs to be built that actually handles that?
Do you want to take it more from an domain expert's point of view?
Sure.
Yeah, I mean, first of all, we are hiring big time. Second of all, I mean, we're growing. And one of the things which really changes in this industry, that if you have 2 or 3 really brilliant people who click, who are aligned on the project. So if you have talent, the problem set up, the problem formulated, the data understanding, they can really run and do much more damage than 100 people at a company working on that for ages. And I think this is the room we have to create. We are not going to expand like crazy. We want the right and smart people who click. I think this is very important. I think breakthroughs will be made in small teams with the right mindset. And I can also personally say the best collaborations I had in my life were with 2-3 people.
But does that scale? Can you scale that?
I mean, you have a few teams of that, right? Too. Yeah.
I'm just thinking about, you're some. I mean, we're going to talk about the competition in a little bit, but at the same time, you've got thousands of employees at across the pond, either in Silicon Valley or even in China, scaling this. I guess my question is, do you not risk that already being unlocked someplace else by the time you get there? Do you get the question?
I think you run much faster with a small team and a very dedicated task and several small teams parallel, but you really set the goal high and you do everything that they have full support to really run at maximum speed with maximum quality.
That puts a lot on your shoulders to find the people who can move that fast.
Yeah, and actually, I totally agree with what you also said, Johannes. And I have the experience also in the past of being a company of 25, then being 300. Yeah. We were so slow. And then famous round of layoffs, and then we were less than 100, way faster delivering. So more people doesn't mean more delivery. Of course, in our case, if we close, let's say, a project and we need a domain expert, I cannot afford to say, yeah, let me now start looking for it. So that's why I know also very often what might come, so that I can start looking for those people, having interesting chats with them, and then as soon as I know we can hire them, then we hire them. But what we are not going to do, which I think is one of the mistakes that many companies did some years ago, is, let's hire 2-3 more, potato. It's like, look, we just hire the people that we know we need. Otherwise, we just don't. Then we end up having unnecessary dramas and way more complexity in the company.
So when most people hear AI, a lot of people think about US-based language models, ChatGPT, Gemini, Claude, trained on vast amounts of internet data. Emmi's different, as you've been describing. The foundation models are physics-based. We've talked about mesh and particle data a little bit here today. But tomorrow, Hanna Virkkunen will talk about, speaking here at TED, we'll speak about tech sovereignty and the importance of Europe developing its own capabilities rather than depending on the US and Chinese tech. How intentional was it for you to build Emmi this way, as a deep tech company with its own models? And do you see yourselves as part of that broader European sovereignty story?
Oh, that's a good question. So first of all, I have to say, I worked at Microsoft. I was close to going to a competitor. I also was thinking about another competitor. So I had my times in big tech. One thing is, do we really want to work for a US company? I think it's a decision everyone has to do. For me, Emmi and going back to university and building these things up is a very personal choice. So I very much believe in tech sovereignty. I very much believe in our beautiful Europe. I very much believe in getting things here done, having the right people. What I don't believe in to just say, hey, we want to kick these US companies from the market and give us money. I don't believe in that, so I think everyone has to prove it. We have to basically not now start, okay, we're just European, we do things European-like, that's enough. I think we have to win with true values, so with performance, with being competitive, being a nice environment. and that's actually very, very hard to build. And obviously, I try to connect with many of our founders across Europe. I mean, I can say from my small team in Microsoft, we were like 7 people. There's like 3 startups coming out. I can name, for example, Caspii, which just raised a 100 million round, and 2 others. And this is the network. This is the momentum you're trying to generate. But yeah, it's difficult. I mean, everyone knows the VC world is different beyond the pond, and obviously we also looking at US and traveling there regularly, and maybe having customer and so on. So it's an international world. We have to stand on our European feet, but with our own rules and with our own way to do it.
Both sides have their own advantages and disadvantages. I mean, I think we hear a lot about speed, again, about bureaucracy, or about this idea of innovation versus regulation, and the judicious balance that sometimes gets crushed from one side or the other, depending on where you're based, right? Whether you're here or there, or, it has an impact. Carlota, let's talk about the European ecosystem a little bit more. Johannes mentioned different countries, different places. You and I have talked about different locations. What can you tell us about both the European benefits in terms of how the playing field gets leveled, but also how Emmi itself is evolving in the European sphere?
I mean, comparing the obvious of US and Europe, generally Europe tries to make things a bit more like in a sustainable way, and maybe in the US they have more a bit this point of optimizing for the next investment round, and this translates also into the way to hire, the way you ask to people to show up at work, and time to invest in there. In our case, we are not actually trying to compete directly with any big fishes, let's say, in the market from a talent point of view, but just try to show our way to work. And this comes with the model that we have at the moment at Emmi AI, trying to hire most amount of people in around European time zone, and we all meet once a month in Linz. So this allows us to hire plenty of people because Europe is big enough. We also helped people to relocate from the US to Europe. We also had cases in the past of some people that decided it's time for me to go to the US and also try that. That's a very personal choice that we always support, either or. And I think the model we chose allows us to find talent way faster. And now we are trying to really combine the face-to-face time, also potentially moving in other places as well, like
other geographies.
Other geographies, So I don't only need to practice my German, but now French as well. Seems that we're going to be in Paris as well.
Why Paris?
Because you can make that joke Emmi in Paris, but nobody finds it funny. So no,
almost worked.
Yeah, I got the reaction the whole week. I'm so excited about that, but nobody finds it funny. As I said,
there is an inside joke about Emmi in Paris that you can ask him later, and this is fine. Why Paris?
No, on a serious note, we have tremendous talent from Paris. So we have a few people hired in Paris, some of our best people. We have 2 French investors. So actually one investor is half French, half Austrian. The market is more ready. So French companies are attractive, and we are attractive to French companies. There is a company that's like Mistral, that the network is amazing. What was going on in France?
Yeah.
And Paris is just a hub, so it's our natural choice to go there, and I think we are all super excited about that.
I have 2 very quick questions that could take all day to answer, but I'm going to ask you guys to try to limit it so we can get to some Q&A from the group of people here with us today. First, thinking about the future, where is Emmi AI in 5 years? Where's the company going? You have a vision. We've established it. We've talked about what you're doing today. We know a little bit about the technology that's being developed tomorrow. Where do you want this to be in 5 years?
I don't know. That's what I want in 2 years. 5 years is too far.
2 years is better than 2 months. So yeah, fine, 2 years.
I think we see a disruption of the $50 trillion industry of engineering happening in the next 2-3 years. And I want Emmi AI to be this disruption. Or to be part of this disruption, at least.
Fair enough. I hope that engenders some thoughts and questions from you guys. But from me too. Carlota, what about you? Where are you in 5? Where is this in 2 years or 5 years?
5 years is uncomfortable. I don't even know what.
My job is to make you uncomfortable.
Yeah. But let's say soon-ish. I mean, sounds a bit classic, but I would just like to have this moment of, yeah, you just walk around with your backpack that has the Emmi AI logo, and then you're at the airport and someone says, I know this. This is a cool place to work. And this happened to me in the past with another company, just on a plane with the logo of the company, and someone sitting next to me is like, huh? I know this is cool, you're in Switzerland, and can I apply? And when this happens, this is such a nice clink magic that, yeah, I would like that we end up in that type of space.
That never happened with my Microsoft bag.
No? Sorry.
We can come back to that because Peter Lassinger, who was was on your board, actually talked about how do you establish the company as a platform and where do you get to. I'd like to open it up here first, but I have one last question, and it's similar to what we were just talking about, but a little bit broader. One of the things that excites me about the future is the ability of artificial intelligence to solve difficult and stubborn problems. Stuff that humans can't solve with the current technology or our own cognitive abilities today. So beyond engineering, beyond Emmi's focus, where your direct focus, let's say, is there a particular scientific breakthrough that you're particularly passionate about that you think is going to happen? And let's use a 5-year to 10-year framework for that. Let's not just say 2. Where are the kinds of models that we need to use to get there? And what are those problems that you're fascinated or interested in seeing getting solved?
I'm quite sure that we will see a lot of breakthrough in medicine. But this has been a multi-billion-dollar industry, and this is kind of obvious to many people. Yeah. I think where we will see also breakthroughs is in material science. That happened very recently, where people started to understand that if we design new materials, synthesize new materials, there's actually a lot of stuff to be gained. I think we will see a lot of breakthroughs in energy. I'm super excited about nuclear fusion. I'm part of the United Kingdom nuclear fusion program. I think plasma energy will be one of the game changers. I actually think that Europe will be the first to get these reactors.
The plasma,
nuclear fusion, yeah, where things come together.
Yeah,
the other way. Yeah, that's my 3 bets.
I'd like to know about yours, about what your bets are. I'd like to know, I think we'd like to know your questions as well. And with the time that we have left, I'd like to open up the floor to questions. We have Larissa, I think, is that your name? Hi, who's in the back, who's helping us with the microphone. And so raise your hand if you have a question for Johannes, Carlota to answer. First question's here in the middle. And please introduce yourself, and don't forget, if you used an LLM, I need to know the prompt.
Hi, I'm Khalid from a startup here in Vienna. We work also like in construction, so it's also engineering. I did use LLM for now. But yeah, my question here is what you mentioned, like that the data for the text models or the image models is abundant on the internet, and you can get that easily. But what was your strategy for the data that you trained your physics models with? Like, did you synthesize the data, or how did it work exactly?
Yeah, so it's a back and forth. So it's, I would say one of the biggest misconceptions is that, and also that always comes up and up and up when you talk with a company, there is this data set and now you train a model and that's it. It's a back and forth. And what we are really doing, we hire the best domain experts, like people worked in Formula One, people who worked in semiconductors at like famous companies. And those people know how to simulate physics, and they really know. And there is like plenty of software, and we also we work together with the state-of-the-art companies who do the simulations, and we step by step start to build up our own understanding of how data needs to look like in order to be, or in order for our machine learning techniques to be applicable. And then we just buy an exabyte of storage, a few hundred GPUs, and then let's go. But that's a few steps on the way. But we actually want to go there where we can really train the big models, and we're not that far. We have like already, I would say internally, if I have to do a guesstimate, we have generated approximately 20 petabytes of data.
Okay. Can I ask another question?
Quick.
Do you see also like a room for these models to participate in the generation? For example, text to text, we have it now, text to images, but like text to 3D models, for example, or like construction or mechanical and so on, like more not mesh models, but like CAD models.
It's a very good question. So I would say the whole engineering pipeline consists of 3 parts. The first is you have to come up with the problem. So you have to come up with the geometry. So what you actually want to simulate, or what's the actual problem you want to be solved. And then this needs to be translated in a computer and modeled. And then from the outcome of the computer, you need to infer what's going to happen. The first part is very much what you're describing, so the interaction of large geometry models, LLMs, and so on and so forth, being creative, coming up with new tools. The second part of the chain is where Emmi AI sits, and then the third part is the deployment or understanding. And ultimately, obviously, this all will come together, but step by step.
Great, thank you.
Thank you. Next question. I think bank sector.
Yeah.
Hey.
Can you stand up and introduce yourself?
Hey, I'm Ivan.
Hi, Ivan.
Hey. No LNM used for my question. No, I just have a quick follow-up question. So regarding the data, I just read the Medium article of your company, and it actually mentions transfer learning and I was wondering if you were able to apply transfer learning, and if so, if you're talking about in-domain or out-domain, and if out-domain, so how, how is it possible to, apply it in your domain?
I am not aware, Mick, that we have Medium article now. Very cool. What I want to answer here is, I think what we are going towards is that we're building models which work for certain dedicated verticals. You can think of it that you build a model which works for cars, and cars in all types of inflow, boundary condition, turbulence models, yada 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 yada. And that's like a vertical that would unlock a lot of industries. I could tell you 15 of these other verticals, but obviously this requires a lot of data, and when then a certain car company comes, or a certain whatever, and they want this, you need actually make the technology, all the data applicable to them, and that needs some sort of fine-tuning, that needs some sort of adjusting to their data. But overall, physics is very similar. It's not the same, but the physics they simulate, the physics we simulate, the physics others simulate is kind of similar. And therefore, in these verticals, you can think not so much of transfer learning, but taking the understanding, and that's what we did in weather modeling, also of all the stuff you've seen, to extract the physics and to fine tune on these projects at hand. Make sense?
Thank you for your question. Somebody up front.
Hi, I'm Tilman. I'm an economics professor from Switzerland. I like the method of simulation. But as a social scientist, I think these simulations deal only with very simple systems like physics. I know you tell us that this is complicated, these cars, etc. But as you're probably aware, there are much more complicated systems which are much more difficult to simulate, which are biological systems or social systems. So I'm wondering what do you think, how we could use AI in modeling really complex or complicated. No, physics is terribly simple because the system does not evolve. There is no evolution. The laws of physics, the basic relations are always the same. You can count on that. The system is not learning. There's no learning, and the car does not change. The car is always the same as you change it. But in social systems, these are the real challenges we need to address with simulations and not, F1, Formula One cars. I want to know what are the chances how the United States is evolving over the next couple of months or years.
You're not talking about simulating something orange, right?
That's a chaotic system. And a chaotic system, by definition, cannot be solved, right?
That's a bit of a disappointing answer. But no, you see what I mean? I mean, these are systems that are really simple. But the challenge for us as a society is not to optimize Formula One cars, but to think how social systems can evolve and can be shaped over time. So, and I would like to know how maybe simulations can be used for that purpose.
So, thanks for the question. It's a great question. First of all, I wouldn't say it's an either or, right? I mean, you can also, it's something to say, okay, I don't care about medicine because something else. What is really fascinating, I can give you two examples. If you try to simulate traffic jams when an accident happens, some equation which is called the Burgers equation with a diffusion coefficient fits that very, very well. And actually you can fit the Burgers equation with two variables to any traffic jams happening, and it basically works. Second example I can give you, when we took the Aurora model and fine-tuned it on the flight patterns of planes, it basically got it right out of the spot. Why? Because it has learned from wind patterns, from solar, and so on and so forth to be adjusted to that. So there is no underlying equations to social interactions, and that's very good because otherwise you could equate what we are doing. But there is certain patterns which are transferable to physics systems, and that is a bit the scale phenomena that. In physics, we have like a 20 orders of magnitude from quantum mechanics to Einstein equation of relativity, and they basically always describe a convection and diffusion term. And these kind of mathematical tools can be used to a lot of social systems, not to all. Obviously, when there is a chaotic component, you just cannot simulate it. You can just pray to God, but that's my answer.
Got time for one or two more? Here in the center, maybe?
Hello, my name is Franziska. I'm running a conference at the Technical University of Munich. And I was wondering, talking about industrial AI, and you mentioned disruption. So I would be interested in knowing your foresight on the future of the so-called old industry, and will industrial AI maybe of help, or will the whole old industry, talking automotive, mobility, energy, be disrupted, and new smaller companies like yours will start on the ground?
It's a good question, and not an easy answer to give, to be honest. I mean, yes, industry will change. I mean, we see the way productivity is changing. We see this big pressure from outside is on us in Europe. If you're not fast enough, if we're not innovate enough, things are just changing. But I would also say that industry has always been changed, right? Like I said at the beginning, when things started to be simulated at the computer, What I think is that the way we innovate has to change. Not the way the industry works, but the way we innovate. And you will still have machinery, you will still have maintenance, you will still have all this type of things, but the way you innovate, it has to change. And it always changed over time, right? As I said before, when people came up with a wind tunnel, they needed the first time they didn't need to take an airplane out in the field to test it. They could do it in-house in a controlled environment. And this innovation cycle is going to change, or it has to. And that's obviously where new technologies come in.
Thank you. While we wait for the next question, I'm going to take one that we've crowdsourced from our social channels. Comes from a friend of mine, actually, named Jürgen Schmidt, longtime friend and self-titled software geek and AI researcher here in Vienna at STRG. He says, anchor attention is clever, but when geometries get really complex, it may hit a scalability wall. Some say you need to move from quadratic complexity to linear, or even rethink the architecture entirely. He says that others, like Mustafa Suleiman, have suggested that maybe the easiest answer is to simply wait for the next generation of computing, including quantum. Right? So maybe we can just wait for it and it's going to happen and solve all the problems that we have. Just don't do anything and just wait for them to invent the next round. My question is, his question is, has Emmi made progress on any of this? Maybe not quantum computing, but on the other question. And how are you tackling the scalability challenge for high fidelity simulations?
So I first of all, it's a great question. I like many people within Emmi and also a lot of people I know within the whole network are convinced that we have the right tools already now to describe the hardest problems and to model that. It's just a matter of how we generate the data, how we store the data, how we train the models, and all needs to come together. But you can train now machine learning models on basically all sort of physics simulations, just a matter of doing it cleverly, having the right people. Our architectures are scalable, or the way we do these things are scalable to the uttermost hard problems. It's just a way of, can we deliver, can we do it? That's the bigger problem. And then obviously at some point we will come back to say, okay, we might need something better. But before that is happening, 10 other things are happening. So I think that you always go for 90%, and I think what you have now is good enough for the next 3-4 years. The innovation is happening somewhere else.
One last quick question before we wrap.
Thank you. So my name is Marin Denkin, and I lead global procurement team at IT company. My question is related to the nuclear fusion energy, and basically I have two questions. What are the today's problems that we need to solve in order to move forward, and how close we are to the nuclear fusion energy?
Great.
Thank you.
So I can only tell you the official numbers. So UK government is building a fusion reactor, the STEP program. It's going into production 2040. They are right on spot on delivering. What the STEP program should be doing, it should deliver energy to a small town. I forgot the name of this town.
Springfield.
That's the official program. I don't know more. I don't know what's like on the material side. There's lots of challenges to be solved, I'm sure, and obviously fusion people now will say, oh God, what is Johannes saying? But where I have a bit of an understanding is plasma physics and how to simulate, because plasma physics is not something you simulate in 3 dimension. You do 5 dimension because it's a phase space of momentum and positions. And so everything which is complicated in 3 dimension is suddenly 5 dimensional. And that's a new barrier in supercomputing, in the AI technologies, and so on and so forth. But that's why I love fusion, because this is a real challenge.
So our next challenge is going to be to wrap this up, and hopefully to carry on this conversation both throughout the next day and a half. Tonight at dinner, tomorrow throughout what I'm sure is going to be a thrilling day of talks about our future, about the present and the world we live in. But for now, I'd really like to thank the two of you for being with us today, for sharing kind of openly and ad hoc a lot of time your feelings about both how you've developed the company that you're creating, but also the future that we're all kind of co-creating at the same time. So I'd like to give you guys a round of applause.
Thank you.
And thank you.